This video does one last example from our section on Euler's theorem, and in this example we're going to use Euler's theorem to solve a linear congruence. Okay, so our congruence to solve is 35x is congruent to 47 mod 24. So the first thing we can do is reduce 35 and 47 to their least residues mod 24, and if you do that you have 11x is congruent to 23, and notice we could choose 23, but if you subtract 24 we could also go with -1, which is a little bit nicer, so let's go with that rather than the least residue. Alright, and then let's get into using Euler's theorem. So what we would like to do is solve this congruent so that we have x is congruent to something, and you can almost think of this as one way to do this would be to multiply this 11 by something so that it would just be the number 1. Alright, and we'll be able to do that if 11, or whatever we end up with there, is congruent to 1 mod 24. Alright, so first of all, by Euler's theorem, we would need 11 and 24 to be relatively prime, so we can check that. Alright, so 11 and 24 are relatively prime, and then that means that 11 raised to the phi of 24 would be congruent to 1 mod 24. Okay, and that part is Euler's theorem. Alright, so part of doing this is figuring out what phi of 24 is. And one rule that we had was that phi of 24 is the same thing as phi of something times phi of something, where the two things are factors of 24. They multiply to be 24, and they have to be relatively prime. Right? So if you can do that, it makes the calculation a bit easier. And you'll notice that 8 times 3 is 24, and 8 and 3 are relatively prime. So this will work. And then that just makes it a little bit easier than just straight counting all of the positive integers less than or equal to 24 that are relatively prime to 24. Now, how many things are relatively prime to 8 that are less than or equal to 8? Okay, well, that would be 1, 3, 5, and 7, so that would be 4 numbers. Right, so phi of 8 is 4, and then phi of 3, there are 2 things less than or equal to 3, 1 and 2 that are relatively prime to it, so phi of 3 is 2. So that tells us that phi of 24 is equal to 8. Alright, and then from all of that, what I can gather is that this phi of 24 is 8, and 11 to the 8th power is congruent to 1 mod 24. Alright, so right now we have 11 times x, just 11 to the 1st power, so the goal here would be to multiply so that that becomes 11 to the 8th power. So we multiply each side of the congruence by 11 to the 7th. And then on the left, we get 11 to the 8th x, and we know that 11 to the 8th is congruent to 1, so that's just x. And then on the right, we can use our normal rules for modular exponentiation to figure out what this is. So let's look at powers of 11, and 11 squared is 121, and mod 24, that's congruent to 1, so that's a nice one to use. Alright, so we'll go with that, and that means x is congruent to -1, and then 11 to the 7th is 11 squared cubed times 11. Alright, since 7 is 2 times 3 plus 1. And then we have -1, 11 squared can be replaced with 1. Alright, and then we have x is congruent to -1 times 11, so that's -11. And then we just want typically the least residue, so if you add 24 to that, then x is congruent to 13 mod 24. And there's the solution. Okay. Now another thing to notice is that since way back in the beginning for this congruence, since we had 35 and 24, their GCD is just 1. Right? So that tells us that this is solvable and it has one unique solution. All right, so we don't need to look for any other incongruent solutions. We found the only one. And then just if you wanted to check this, you could go ahead and just plug 13 in for x, and then just verify that that does solve the congruence. And that's it. All right, so to summarize, we just reduce everything to its least residue or a small negative number if possible to solve the congruence. Next, you look at the a, which in this case was 11, and you find a to the phi of m, so a to the phi of 24, which was 11 to the 8th, and then you just multiply by whatever you need to on the left to get that 11 to the 8th. All right, and then that solves for x.